So hi guys, we are going to learn about the classical information theory today, just the important bits. So generally the quantum information theory is a little bit different from what we have in the classical information theory, but it forms the baseline for whatever we are going to learn in the future. So that's right. So that's the reason why we need to know a little bit about what the classical information theory tells us. So let's get started. First of all, let's try to understand what information is. So it can be, you know, it can be a combination of any kind of, it can be a combination of symbols, numbers, digits, alphabets, whatever. Okay, which may, provide you with some kind of meaningful message. Okay, so it's not important like what information actually is, because the definition actually differs. The physical definition of information is very different from the information that we deal it in our day-to-day lives. But what's important is that how we encode this information, right? So let's say that we have just two symbols. Let that those symbols be 0 and 1, just for an example. Okay, so we have two symbols, 0 and 1, and and we want to encode some message. Okay, so the question is how many bits will be required to encode that message. Remember that each bit can actually take either 0 or 1. Okay, so now since we know that there are two possibilities for each bit to have either 0 or 1, one bit can actually represent two different messages. Similarly, two bits in combination can represent 2 into 2 4 different messages. Three bits in combination can represent 2 into 2 into 2 3, 2 cube different messages. So in general, the if you have a message m, then the number of bits that are required to encode that message is basically 2 to the power n, right? uh, Sorry, yeah. So basically, in order to encode a message m, okay, we read at least n bits, which is so I mean you can have even more than n bits. Okay, but that would not be a very efficient way to encode this message, because many bits will be not used. So yeah, so I mean the minimum number of bits that you require would be 2 to the would be n. Okay, and there's a very interesting way to actually look at this equation, because if I take log on both sides of the equation, then this becomes n log 2 equals log m, right? And here I'm taking log with base 2, so this log 2 will become 1, and this would basically be uh, n equals log m. So it basically means that if you want to encode, so if you have a message and you want to encode that message, then the number of bits n is basically the value of the log of m. So just for an example, if you have, let's say, if you have a if you're trying to develop a language which communicates 256 different kind of messages. Okay, so how many bits would be required to represent such a language? That would be log of 256, which is 8, right? So that's what this equation talks about. Okay, now the question is, okay, fine, I mean we have messages, we have bits and all, and everything is good, but what about information? Okay, how much information does something has? Okay, so, so Shannon came out with so the idea behind this is like this. Let's say that you have a message, okay, and if that message is like let's say that you have a sender, okay, and the sender every day sends just same email each and every day, then that email does not contain more information, that does not contain enough information, because it just sends the same email each and every time you read that message, right? But on the other hand, there's a sender who sends different kinds of emails every day. Okay, So depending on the utility, that email will definitely contain more information than the email which from the sender who sends the same kind of information. So in a way, information is basically the uncertainty or the randomness in the message or the signal that a sender is sending, right? So we can, so Shannon said, gave us the equation that information we can write it as minus of log p, where p is the probability of finding a particular symbol, and yeah, and the negative logarithm of that is basically the information. Now you might be wondering what is the utility of this negative sign in front. So see, this probability p is a probability, so it will be a fraction and it will always be less than 1. So for example, if you have probability p as 1 by 2, then log of 1 by 2 will be log 1 minus log 2. So that would become negative and information can't be negative. So in order to, in order to deal with that, you have the negative sign in front. So that's the equation that he gave for basic information. But we need to formally define what what an information is, or how much information a message has, right? So we can divide in a more formal way like this, that let's say that there's an x. Okay, x is a random variable, uh, and h is basically the entropy. So you can write this as uh, pi log of pi. Okay, so this is how the entropy is defined. So yeah, so for a message, this is what the entropy is going to be. I can, so let me give you some example in order to make you understand this. Let's say that we have a message which is 22222. Okay, so and we have another message which is m equals to 232323. Okay, so how much information does this message contain? Okay, so if you calculate the entropy for this message, then that would be minus. Okay, because there's just same symbol and the probability of getting that symbol is 1, which is 100%, because all of them are just 2. So the probability is 1, so it would be like minus 1 log 1, which is going to be 0. Okay, and now coming to this one, if you have the value of m as 232323, then it means that the probability of finding a 2 is 1/2 and the probability of finding a 3 is 1/2. So the entropy, you can write it as minus 1 upon 2 times log of 1 upon 2, and then minus 1 upon 2 log of 1 upon 2, right? So this is going to have some answer. We are not really interested in that answer right now. Okay, but I wanted to make a point which I'm, so for which I'm going to take another message. Let's say 234 234 234. So there are three symbols and each of them, the probability of finding them is like 1 by 3. So the entropy in this case is going to be minus 1 upon 3 log 1 by 3. Then you have minus 1 upon 2, sorry, minus 1 by 3 log 1 by 3. Then you have minus 1 by 3, you have log 1 by 3. So the reason why this is because there are three symbols and all of them have the same probability of 1 by 3 to be found in the message. So again, this is going to give you some answer. We are not interested in what answer it provides us. The only thing that I want you to notice is that the value of this will be higher than the value of this, right? Because if you calculate it, you will see that the value of this is greater than the value of this. It will be like something like 1.5 or something. I'm not getting, yeah, whatever the answer is, the important thing to realize is this is greater than this, because there is much more randomness in this message than there is in this message. And that's the reason why you have a higher entropy for this message. And when you say higher entropy, it means that it's going to contain more information than the message that we had earlier. Okay, so that is in short about what Shannon's entropy talks about. Now let's talk a little bit about two other things, which is which is uh, relative um, relative entropy and uh, conditional entropy. So if you start with relative entropy, so in relative entropy we try to calculate the value or the entropy of a random variable x relative to the entropy of the random variable y. So for example, you have h and it's represented by two bars, okay, and y. This is which means that the relative the relative entropy of x with respect to y. Let's first define the probability distributions as well, just for clarity. So let's say uh, x has the probability distribution of p and y has a probability distribution of q, right? So the relative entropy of x, the relative entropy of x is going to be um, yeah, so the okay, for some reason it's not coming up, so let's define this as this one and y in q. Okay, then the relative this is going to be minus of log I'm sorry, minus sum of p log it will be p upon q. Oops, p upon q. And you can understandably this is nothing but this is nothing but p log p minus sum of p log q, right? And we know that this minus p log p is nothing but Shannon's I mean the entropy for the for x, so we can write it as the entropy of x minus sum over p log q. Okay, so this is like this is the relative entropy of x with respect to y, which is nothing but the entropy of x minus this uh, yeah, this expression, which is sum over p log q, where q is the distribution for y and p is the distribution for x. Okay, there's another thing, which is conditional entropy. So conditional entropy H represented by a single bar, different from the relative entropy where it was represented by double bar. It goes something like minus some j uh, probability of xj given yi and times log of probability of xj given yi. Okay, so this is the conditional probability that we have. uh, so the difference between the relative entropy and the conditional entropy is this, that when we talk about relative entropy, we are talking about the the entropy of x with respect to y. But when we are talking about the conditional entropy, we already know the probability for a symbol in the message, so which is yi. So we already know what yi is, and we are just calculating the value of x with respect when yi is provided. So yeah, so what this conditional entropy basically represents is that you're trying to find out the entropy x given that you already know the entropy y, okay, or at least the probability distribution behind it. And the relative entropy goes like you are trying to find out the entropy of x given that uh, you are not, I mean, you have the entropy of, you do not have the exact information about the entropy of y, but you do have the probabilities. Okay, so that's what relative and conditional, you know, uh, entropy goes. So this is all I wanted to discuss from today's lecture, which was related to classical information theory and entropy. Apart from that, going forward, we would require understanding of the probability. So if you because even though quantum probability, the way we use probability in quantum mechanics is kind of different from the classical probability that we might have worked on, but anyways the baseline is required. So if you remember, then well and good. Otherwise, I suggest you to brush up, and see you in the next lecture.